Good afternoon, ladies and gentlemen. I would like to start with our webinar with the name of Steel for Sustainable Bridge Infrastructure with Low CO2 Footprint Now and in the Future. The main aim of this webinar is to provide insight on existing and future solutions from steel for low carbon and sustainable steel composite bridge structures. Before we will start, I would like to introduce myself and the colleagues who will be speakers for today. My name is Pavel Riáček and I'm from the Faculty of Civil Engineering at the CTU in Prague in Czech Republic, and also a chairman of the Bridge Committee. We have in total 3 speakers. The first one will be Mike Thibault, who is an engineer for bridges and ArcelorMittal Stelligents, and who is responsible for the technical advisory and promotion of small and medium span bridge steel span composite bridges. He is also currently vice chairman of the ECCS Bridge Committee. The second speaker is Madhu Sayatan from SSAB. He has 19 years of international experience in technical, business, and strategy development. He is working currently in the SSEB. And the last speaker is Tobias Lennart, who is working in the marketing and technical support for wind power and steel construction at Dillinger. And currently, he is the head of the Department of Wind Power and Construction. Before we will start with the webinar itself, I would like to say a few words about the IAPSE. The global IAPSE mission is to exchange knowledge and practice of structural engineering worldwide, and it covers all aspects of structural engineering, structures, and the materials. And at this moment, IAPSE has more than 3,200 members in 100 countries around the world. IAPSE is organizing many activities. We are now organizing this webinar for you, and we also expect several conferences and congresses. I would like to especially mention the upcoming IAPSE Congress in New Delhi, where the registration is currently opened and you can join this interesting event. IAPSE is also publishing many journals and bulletins, for example, Structural Engineering International, very interesting and challenging journal. And there are also many bulletins and conference proceedings. IAPSE has many activities in national groups. There are many task groups in many countries. For example, in case of task groups, there are more than 40 of them, and we have about 6 technical commissions. You can see the list on this slide. And also the IAPSE is organizing many activities for young engineers program. For example, within a month approximately, there will be a young engineers colloquium in Dresden, organized together with the Czech Republic and Germany. You can see some of the activities from the national groups events on this slide, which is showing that the activities are quite interesting, and it covers many areas of structural engineering. And last but not the least, there is a possibility to use the knowledge and the IAPSE library. You can see the IAPSE e-learning program here on this website. So that's all for the introduction, and now I would like to give the word to Mike Thibault so that he can start with his presentation. So Mike, floor is yours. And please, I would like to mention before the beginning of this lecture that it's possible to have questions, and please write your questions in the folder Q&A in the Zoom, and the questions are being answered at the end of the whole webinar. So we will have 3 presentations, and at the end of all of them, there'll be enough space for our questions. So, Mike, please, you can start with your presentation.
Yes, so hello everybody. Thanks, Pavel, for your nice introduction. So in the upcoming 26 minutes, I will talk about steel for sustainable bridge infrastructure. And I will present you products which are already available, and here especially the umbrella brand for our sustainable steel, which is called X-Carb. Before I start, I would like to give before I start, I would like to give you a small overview on the topic we are talking today. So starting from the big picture, and here we can see that over the last 8 years, starting in December 2015 with the Paris Agreement to limit the temperature increase to 1.5%, there are many events that were coming. And of course, we see that there is an emergency to react on the climate change. And that's why also as a steel industry, we have the responsibility to decarbonize and to reduce our footprint. And starting with the Green Deal in December 2019 to make Europe the first climate neutral continent by 2050, ArcelorMittal commits to be net zero in 2050. If we have a look at the steel, it is critical for the transition, and it is a backbone of the net zero economy, without any doubt. As we could see, it plays a core role in the electrical vehicles, and also in the infrastructure for renewable energy, like wind turbines or solar panels. But it also is important for the next generation of the high-performance building and to help to reduce the carbon footprint of the buildings. And which is true for the building is also the case, of course, for the infrastructure, especially also for bridge infrastructures of the future. And here the steel will play an important role in the future. And already today, steel is the most circular material seen globally, with a recycling rate above 85%. So we can see that there is a potential for steel. On the other hand, the steel production is also responsible, globally spoken, for about 8% of the CO2 emissions. So this is, of course, a significant number, whereas our responsibility to reduce our carbon footprint. And how this can be done, I will present you this from the point of view of ArcelorMittal. So the action plan to decarbonize steel production. And in 2019, ArcelorMittal published the first group climate action report, where it stated that ArcelorMittal Europe will reduce its carbon emission by 30% by 2030. In 2020, the European Climate Action Report was published, and here ArcelorMittal sets the net zero target until 2050. And then 2 years ago, in 2021, the second group Climate Action Report was published, where on the global scale, so on the global scale of the group, ArcelorMittal commits to reduce its CO2 emissions by 25% until 2030, and on the European level, up to 35%, so an increase of 5% compared to the initial target in 2019. And the question is now, okay, how do we get there? And therefore, let's first of all have a look, what are each steelmaking route, which are commonly used to produce steel, what is the carbon footprint of each of these production routes? Starting with the blast furnace route, where the main input is coal and iron ore, and the main sources of CO2 is coming from the chemical interaction between the coal and the iron ore during the reduction process. And the emissions are direct emissions coming directly from the steel production. And the emission lies between 2.25 and 2.8 ton of CO2 per ton of steel produced, including the rolling of the product. Then we have the electric arc furnace, where we use scrap to produce the steel. So the main CO2 source in this case is the purchased electricity that we need to heat up the electric arc furnace. So these are indirect emissions, because we do not directly produce the electricity that we will use in our plant, but we will purchase it. And those emissions, of course, lower. They lie between 0.62 and 0.85 tons of CO2 per ton of steel produced. And then we have the third route, which is a direct reduced iron route, followed by an electric arc furnace. Here we use in fact, iron ore that is reduced by, at the beginning or at time being, by natural gas to form what we call sponge iron, which is not a liquid pig iron anymore, but which is a solid material in form of pellets that in a subsequent step will be melted in an electric arc furnace. And here we have then as a CO2 source mix of two emissions, so from the reduction and from the purchased electricity for the electric arc furnace. And here the emissions lies between 1.12 and 1.35 ton of CO2 per ton of steel produced. And now, starting from this, how can we now achieve the target, at least in 2030, to reduce the CO2 emissions by 35%? And we have here two breakthrough carbon neutral routes that we identified. The first one is what we call the smart carbon rule, which is a carbon neutral steelmaking route that uses all clean energy. So circular carbon, but also CCS, so carbon capture and storage, as well as clean electricity. And this within the high temperature controlled reduction environment of iron making. And as you can see on the pictures on the right, in the first phase, the smart carbon will primarily use the circular carbon and the CCS technology until 2030. And then on longer term, it is foreseen to also work with hydrogen. The same is for the second breakthrough technology, with this DRI-based route. So in the first step until 2030, this route will be mainly based on using natural gas as a reductant element. But on long term, it is foreseen to replace it by hydrogen. And then we have a third one, which will only be applied in short term. It is to increase the use of scrap in the blast furnace route to reduce also the CO2 emission in the blast furnace by increasing the content of scrap. So these are the technologies that we identified to become a carbon neutral. Now the smart carbon route, what is ongoing there? One example of the smart carbon route, one project is the Torero process, where we turn toxic wood and plastic waste into biocoal. So we drive this waste and we torrefy it to produce a biocoal. And this biocoal will be used in the blast furnace to reduce the coal coming from the mines. And at the moment, we have an industrial scale demo plant in Ghent, in Belgium, with 2 reactors, with a producing rate of 40 kilotons of biocoal per year. And it is expected to start now in 2023 for one of the reactors. And this will help us to reduce the CO2 consumption already in the blast furnace corresponding to the smart carbon route. Then on the DRI route, we have here in the first step to use this technology and to replace a natural gas, which is currently used as a reductant element, by hydrogen. And in the first step, this will be blue hydrogen, so meaning hydrogen which is produced by electricity, not coming at 100% of renewable sources. And this will be the case in the second step. So to switch from blue hydrogen to green hydrogen, so hydrogen that will be produced coming from electricity of 100% of renewable sources, mainly solar and wind. And by doing so, we can achieve this target of being net zero in 2050. So this is the long-term perspective, the step 2. And by all these efforts that we are already planning and doing, and which are currently ongoing, we launched what we call the X-Carb brand. And this is designed to bring together all of our reduced and low and zero carbon products and steelmaking activities, and to put on the market a steel product, which has already a low emission embodied carbon footprint. And this is working so under the umbrella of the X-Carb brand. And this is what I will present you in the upcoming slide, what this is. So starting first of all with the X-Carb recycled and renewably produced. X-Carb recycled and renewably produced is the brand which covers all the steel which is produced in the secondary production route, so meaning by electric arc furnace. By using 100% of green electricity, purchased via guarantee of origins in the European system, and to feed with this energy the whole production line of steel, and to use up to 100% scrap. And by doing so, we can reduce the carbon footprint of the product down to about 0.3 tons of CO2 equivalent per ton of steel product. And this is significantly lower than the current average of steel production, which lies at 2.3 tons of CO2 emissions. And this is the ideal, and this is how it works. So what can we guarantee, in fact, to the customer? As I said, this X-Carb recycled and renewably produced is certified, and this certificate guarantees that the electric energy which was used to make the steel is coming from renewable sources, mainly solar and wind power. And the certification process has 4 steps. So in the first step, we purchase renewable electricity, as I said, via the guarantee of origin in the European system. And then we have a follow-up of this order system, so that we have the guarantee of origin to produce the steel, and that later on it will also be eliminated from the system, not to use it twice or several times for the same steel. And then for the step 3, we have the delivery of the material documentation with the X-Carb certificate, and finally the delivery of the final product to the customers. So this is a product which is already on the market and available. And for this, we also have environment product declaration, which are instruments to communicate publicly about the key environmental impact of specific products. And these EPDs are based on life cycle assessments according to the corresponding standards, and they are independently verified. And here we have an EPD for our hot rolled sections with a value of 333 kilograms of CO2 equivalent per ton of steel. We have them for the sheet piles which can also be used, for example, for the abutments for bridges, where we have a value of 370, and we have it for the rebars, where we have a value of 300 kilograms of CO2. Now it is like it is. We know that each country can also have its specific rules and criteria. So a general EPD will not be sufficient to cover the market. For example, in France, they have an EPD which is called FDES. It covers additional, let's say, steps in the use of steel, like, for example, also the transportation from the steel product from the mill to the construction site and the mounting on construction site. And here we have a value also of 388. We have an Eco Sheet Pile Plus EPD for sheet piles in the US and also for the Dutch market. So to comply with this specific criteria on each market. Then we also have this brand X-Carb recycled and renewably produced for our heavy plates. So these are plates which are produced by slabs. The slabs are produced in electric arc furnace route using 100% of scrap and 100% of green electricity. Then the slab is transported to the rolling mill in Gijón in Spain by ship and road, where 90% are represented by the ship transportation. And then in the mill, it will be rolled to the final product, to the final plate. And here, if we sum up the emissions, we will lie between 0.9 and 1.1 ton of CO2 for the product stage A1 and A3, so manufacturing and producing of the product. And which is now coming soon is that we will also have an EPD for those heavy plates under the X-Carb brand. And this is foreseen in Q3 2023, in addition to the EPD which we have already for the plates, but for the plates which are then produced by the blast furnace. I will come back to this in a second. And of course, you will also get a certificate, as it is the case for our hot rolled sections and sheet piles. Then for products which are not coming from the electric arc furnace, but which are produced via the blast furnace, we have also a brand which is called X-Carb Green Steel Certificates. And these certificates can be purchased alongside any steel sold by ArcelorMittal Europe flat products, because mainly the flat products are produced in the blast furnace right now. And the CO2 reduction based on the certificate are coming mainly at the moment by reducing the fossil coal consumption in the blast furnace by replacing it by natural gas, and also by re-injecting the coke oven gases again back into the blast furnace. And later on, we will then, based on the smart carbon route, as I explained in my former slide, like the Torero project. This is independently verified by DNV, and these certificates are to be understood as a transitional tool rather than a final solution. because it is sure that we can still enhance our reduction of our CO2 emission in the products. And that's why it's only a transition right now, but to make our customers already part of the efforts that we are doing to reduce our CO2 emissions and to make them also part about this reduction for their specific projects. Then, which projects are available? If we come back to the X-Carb recycled and renewably produced, so the steel produced under the electric arc furnace, we have the hot rolled sections and heavy plates. And for the hot rolled section, so all the steel which are also in the sales program are available under the X-Carb brand, recycled and renewably produced. And we have a whole range of these products, so coming from an EPE, going to an HL, which is a very high hot rolled sections with a height of 138 millimeters. And then also our HD sections, also called Zumbo profiles, with a flange thickness up to 140 millimeters. And what is new since 2019 is that we have now also high-strength steel, not only S460, but also S500M. And since 2019, we also offer hot rolled sections in weathering steel, in high-strength steel S460, up to a flange thickness of 63 millimeters. And since 2021, as I said, they are also available under the X-Carb brand. Now, where can we use these hot rolled sections in bridges to reduce the carbon footprint of the bridge? So they are very economic and sustainable for small and medium span bridges, mainly for span ranges between 10 and 45 meters. So they can be used in filler beam bridges, in steel composite bridges. You can also do some fancy projects like using the composite dowel, where you obviously cut dowel in the hot rolled sections to have a composite action between the concrete deck and the steel. And they can also be used in the arches of network arc bridges. As you can see it here on the picture, this is a bridge in Poland, which has been realized, and we have several such bridges already done, but also for other standard bridges like trusses, true bridges, or temporary bridges, where they can be used in a very efficient way. Then here we see the range of the heavy plates that is also will be soon available under the X-Carb brand. So mainly covering non-alloyed steel, normalized steel, thermomechanically, and also weathering steels. And for the weathering steels, we are currently working on putting on the market the S355K2 steel grade with the certificate NFRCA in France up to 100 millimeter. And also we are working to develop weathering steel in high-strength steel S460 up to 30 millimeter. Why high-strength steel is important, I will show you this in the coming slides when I talk about recent bridge project which has already been realized using the X-Carb brand. There is a Europe longest cycle bridge which is made from X-Carb recycled and renewably produced steel. This is a bridge, a pedestrian bridge, which is realized very close to one of our plant in Belval in the south of Luxembourg. And the key element for the public authorities to go for this solution was the carbon footprint of the project. Here we can see on the left a picture of the inauguration of the bridge in the presence of the Ministry of Environment and Climate Change of Luxembourg, Joël Welfring, which was very proud to have now also helped to realize a project with reduced CO2 emissions by using this steel. Then we have here the first European road bridge, which is called the Osmolice Bridge in Poland, which combines the X-Carb recycled and renewably produced steel together with weathering steel in high-strength steel S460. Why was this important to have these choices? First of all, the investor would like to have an easy and not so heavy solution. That's why he go for a solution, a composite bridge with hot rolled sections. And by using a weathering steel, there was no need to put a painting on the bridge, because for weathering steel, we have this auto protection, this patina, which will form automatically and ensure the corrosion protection. And so we do not need to reduce or to change the painting, to redo the painting over the lifetime of the bridge. So also the maintenance efforts will be reduced. And of course, we have no detrimental negative impact on the environment coming from the painting. And by combining it then with the X-Carb brand, of course, we can further reduce the CO2 footprint of the solution. And this was the driver to go for this solution. The bridge has been realized 4 weeks earlier than foreseen in the planning, because also the construction was quite easy. And by using high-strength steel in combination with weathering steel. We could also have light solution, because for weathering steel, as you know, you might apply for a thickness allowance to consider the corrosion losses over the lifetime of the bridge. So, and in your design, you have to reduce all the thickness of the surfaces which are in contact with the environment. And of course, in this case, you would end up normally with higher profiles. But if you combine it again with S460 steel, you can compensate for this effect. And that's why it could be very attractive to use this solution. And here we'll show you a small case study, which I have here, which is in fact a bridge Rosières-aux-Salines in France, which was initially foreseen in pre-stressed prefabricated concrete girders. The bridge has a total length of 108.25 meters, and it was foreseen in 4 spans between 20 and 28 meters roundabout. The slab was an in situ concrete slab C3545 with a thickness of 21 centimeters. And the total tonnage of the girders, only of the girders, was 10,050 tons. And as we also offer technical assistance in the design phase, so in the pre-design phase, we also worked out the solution using composite solution between hot rolled sections and a concrete slab. And this was finally the solution what was retained for the construction. So the total length remained, of course, untouched. But by using the composite solution was a solution where we put 2 hot rolled sections welded together on the upper and lower flange to form a box section out of hot rolled sections, as you can see here on this picture. And this can be realized in the workshop. And then by doing so, we could also reduce the number of spans down to 3, with spans between 30 and 38 meters. And we had 4 box sections in HE, 1000 profiles in steel grid S460. Again, the high strength steel to reduce the section size. Colleague Tobias Lehnert will also make a small insight in using why it is useful to use high strength steel, because also the material consumption of your project will be reduced. And you will have then the concrete slab was an in situ concrete slab based on the pre-stressed concrete filigree, so prefabricated pre-stressed concrete elements, with a variable thickness between 22 and 40 centimeters. And the total tonnage of the steel girders was 260 tons, so a little bit less than for the concrete solutions. And also what we're using was concrete cross-beam technology at the piers. So this allows us to deliver the steel beam in span lengths, so and in one single piece. So meaning that there was no welding or bolted splices necessary on construction sites. So also facilitates, in fact, the execution of the solution on construction site. If we have now a look at the case study we did in LCA to compare a little bit the global warming potential, so the CO2 emissions of the solutions, and we cover here all the stages, so A1, A3, which covers the construction materials, not only the steel girders and concrete girders, but also the equipment, the caps, and so on, the transport to construction site, and also the construction and installation process, as well as a material replacement and refurbishment, whereas this is a very insignificant amount, as you can see in the diagram, the end-of-life scenario, and we sum it up. And we can see for the pre-stressed prefabricated concrete girders, we have a tonnage of 1.36 tons of CO2 emissions. And by the solution which has been retained and realized is a steel concrete composite deck with longitudinal girders, box girders, we could reduce the CO2 emissions by 12.5%. And if we would have used the X-Carb steel recycled into newly produced at that time, was still not possible, we did the LCA, we could even reduce it by 22.8% compared to the initial concrete solution. And this is to show you a little bit that, first of all, in the diagram, you could see that it is stage A1 and A3, so the construction materials, which has the highest amount on the CO2 emissions, highest impact, and that by adapting the solution and to optimize the solution, not only from a technical point of view, but also from carbon footprint point of view, that you can achieve significant savings. And here you could see the bridge as it has been realized in France, so close to Nancy. You can now see this bridge so it's already finished, so in action, really. And that was from my side, so I thank you for your attention.
Thank you very much, Mike, for a very interesting presentation. And I think that now we should move to the second speaker, to Madhu Sayatan. So please, Madhu, you can start. The stage is yours.
Mike, could you please stop sharing? Then I could share the screen. Yeah, thank you.
I think that you are muted.
Could you hear me now?
Yes, now it's fine.
Perfect. Sorry for that. Presenter's curse happens sometimes.
Sorry, but still you are muted. Or I don't hear you.
Probably because when I start sharing the screen, something happens.
Yes, exactly.
Maybe we could move to Tobias and see if he can fix my ID issue then.
So let's continue. So we will start with the third presentation and we'll come back later to Madhu. So please, Tobias, you can start with your lecture.
Okay, yes, just 1 second. I will share my screen and see if the same happens or not. So can you hear me and see my screen?
Perfectly.
Okay, cool. Okay, yeah, thank you very much, first of all, for the kind introduction and for the possibility to speak here, to give a presentation. My name is Tobias Lehnert. I'm heading the department marketing and technical support for the areas wind power and construction at Dillinger. And as you may know, Dillinger, we are a heavy plate producer. So we are a steel company producing only one product. It's only heavy steel plates. So my presentation today is about possibilities to reduce the CO2 emissions in bridge building now and in the future. And yes, possible ways to reduce CO2 emissions and improve sustainability. If you've seen also from the presentation of Mike, steel as such is a very sustainable material with its possibility to be 100% recycled. So I would say being a steel guy, first choice, of course, is use a steel bridge. But of course, what then? What could be done then? So it's naturally that the idea is, okay, let's use low CO2 emitting steel. And Mike showed nice examples how this is possible. But bridges also very often need the product heavy plate. So we have a lot, especially for large bridges, they're built out of the steel product heavy plate. And traditionally, the steel product heavy plate in Europe, but also globally, is mainly produced by the primary route, so by the blast furnace. And as it was explained in the last presentation, this primary route, the blast furnace, using iron ore and having the iron ore reduced by coal or coke in the blast furnace, emits a lot of CO2 emissions per ton of steel. And it is currently not possible due to quality reasons, but also just due to the availability of scrap, that the whole steel industry switches to a secondary route. So even in the future, we will always need a primary route which brings new primary steel in this circle of recycling. So that means that for the product of heavy plate, the availability is currently quite limited of steels with low CO2 footprint. And that means, yeah, we also have to transform the primary route towards less CO2 emissions. And Mike explained also the possibilities there, for example, by going to a DRI production, direct reduction, plus an electric arc furnaces. So there exist several routes in the steel industry which are currently followed. We have also a brand for our transformation. It's called Pure Steel Plus, and that's our way to transform our company to a low-emitting steel production company. And I will just shortly show, because it was already explained before, what is the initial situation in such a blast furnace mill. So we have a coking plant, we have a blast furnace, and the basic oxygen furnace, and the emissions are mainly coming from the blast furnace, where we need the coal to reduce the iron ore, so to take away the oxide. And if we combine the C from the coal with the oxide from the iron oxide, we will end up with CO2 emissions. And then in the next step in the steel plant, it's a basic oxygen furnace. So we blow oxygen on the liquid steel or iron in this case, and then take away again the C, the carbon, and we again have CO2 emissions. So these two processes are responsible for most of the emissions in such a primary, currently blast furnace primary route. And it's not only the coal is not only needed for heating, it's actually a chemical reaction. So we need the coal as chemical reducing agent in this process. So it's not that easy to replace it, but there exist some possibilities to do so. But that means we have to transform all of these production steps in our plant, which is, if you look at the full production chain, it's quite a bit. It's more than half of the plant. And if we speak of transforming, it means actually, it's a nice word, transforming. In the end, it means, take it away and do something else. So that has an impact on the entire production chain. And it's clear that such a process, it needs some time to change this new production. And that means, of course, that for bridges built of heavy plates, currently to go to physically produced heavy plates with low CO2 footprint, it's currently quite limited possibilities. But that will, of course, change when the production is replaced by DRI production, for example. But generally, of course, steel industry is doing a lot in sustainability. Dillinger, we received, for example, the Gold Award in EcoVadis. We are listed as Carbon Disclosure Project. We are also signing the Science-Based Target Initiative to declare the commitment of our roadmap to be aligned with the climate goals. So these are very important points. But as I said, in order to change and to transform, we need to have a plan, we need to have a roadmap, and we need to change our production. And here in Dillingen, we are doing our transformation in 2 phases. So in the status quo, we have 2 blast furnaces in our production and several basic oxygen furnaces. And the phase 1, which will be happening until 2030, we will shut down 1 blast furnace and build 1 DRI plant with electric arc furnaces. So already a big portion of the production will be changed to this new production route. And in phase 2, then also the second blast furnace will be shut down. So that means that in a certain time, in some years, there will be, and because not only us have these plans, also other steel mills, other steel companies have similar transformation plans. So the availability of steel produced by new low-emitting routes will increase over time significantly. But as I said, yeah, it may be not possible for all products to get already the lowest CO2 emitting steel. So what else can be done now already to reduce CO2 emissions in a bridge construction? And there are several starting points where you can decide for a more sustainable way. And one was already a bit touched by Mike's presentation, is the use of higher strength steel. This is important in this bridge design, an important decision in the bridge design, which affects the sustainability of the project. So what would be benefits of using higher strength steel? This is just an example, a very easy example. If you calculate from S355 to an S460, in an ideal case, a thickness reduction of up to 30% is possible. This is an ideal case, but in reality, usually you also end up with 15% or up to 20%, which you can save. And this, of course, has multiple effects on the CO2 footprint. The first most significant point is, of course, less steel. So that means less CO2 emissions. But on the other hand, the component weights are lower. You can use bigger assembly units, less truckloads, less traffic on the construction side. Lighter constructions also means lighter foundations. So by that, adding further effects, which will impact the CO2 footprint of a project when using higher strength steel. And so this is a very resource saving, because the best thing is, of course, to avoid the material. And it is already ready available. And the good thing is, it is also cost efficient. So on one thing, you have reduced material cost, but additionally, you will also benefit from reduced overall welding cost in the fabrication of such a bridge, because the welding cost, they grow over proportional with the blade thickness. That means if the blade thickness can be reduced, you have reduced weld seam volume, and that has a significant impact on the welding cost. So using higher strength steel in a bridge building is very sustainable and highly economical efficient. So it's a very good choice. Another point where we could reduce CO2 emissions already nowadays is in the maintenance. For example, by the usage of weathering steels. As it was already explained in the presentation before, weathering steels, they build their own patina, which saves them from further corrosion. So no repainting is necessary here. This has, of course, several effects overall in maintenance intervals and things like that. But one thing is also, if it is, for example, a motorway crossing, it's less construction, less traffic jams. And there was a study done in the ESPRI project, which pointed up to 5% less CO2 emissions if a motorway crossing is built by a weathering steel, because of the avoidance in traffic and by that CO2 emissions. There are some design application restrictions needed, but this can be found in the new European design guide. So it is already ready, available to use these weathering steel grades. In the past, there was the weathering steel grades, the usability was quite limited, because there were just limited steel grades available. So let's say the steel strength was limited to only S355 steels, but also the toughness levels were limited. So especially really bridges where you need maybe higher strengths or where you need higher toughness levels were not possible in weathering steel grades. But with the new revision, this is no problem. We have a wide range of weathering steels now available, also up to 460 steel strengths, and also with minus 50 degrees Sharpie impact. And very important, also with the delivery condition, thermomechanical rolled. And so nowadays we have a higher strength weathering TM steel defined and applicable. And here again, it is very important that it is now allowed to use thermomechanical rolled steels, because these TM steels, they again have benefits, as they are, one thing is in the production, in the steel production, but also later in the fabrication, in the bridge building, in the workshops. They can be welded without, or at least with a significant reduction of preheating. And this is again, of course, energy which can be saved, and that means also CO2 emission. Besides that, it's also very important for job safety, because you do not need to preheat. And if you have a look on the pictures shown here, you can imagine that preheating the structures and welding then is quite hard work. So if you can avoid the preheating, it also is very good for job safety. So there is a possibility, let's say, to somehow combine all these things, which you can do nowadays by, for example, using high-strength weathering steel. And there is, I will show you one example. Oh, no, sorry. First, these high-strength weathering steel grades, there's also a brand steel from us. It's a DWT 460, which gives then again additional benefits on the carbon footprint, equivalent. So again, better weldability for the fabrication, and it is available in very large dimensions, very wide widths. As all our plates, we can deliver plates up to 4.6, even 5-meter widths, plate weights up to 42 tons, and that again avoids welding, and by that it is also good for the CO2 emissions and the sustainability. And here's one nice example. It's the Carrington Bridge in UK that was originally planned by S355 steel. In the end, it was realized with S460 thermomechanical rolled steel. It was planned as a 6-span bridge. It could be then produced in a 3-span bridge with 6 weeks reduction in construction time. And very important, 3 piers could be avoided, and 50% less steel was used. And overall, you can imagine that has a significant impact on the CO2 emission if you can avoid the concrete of the piers and the foundations, as well as the steel emissions. We do not, unfortunately, do not have an LCA calculation for this project, but I think it's quite obvious that it has a much significant impact on the CO2 footprint. So yes, with this, I want actually to finalize my presentation, a quick overview of possibilities where you can, together with the steel industry already now, but also in the future, improve sustainability and CO2 emissions of your bridge project. And I would want to close with something that we just together, let's imagine a bridge building in some years will be built, minimized material consumption by high-strength steel, and the steel that is still necessary, produced with a very low carbon footprint, less fabrication energy because you can use large dimensional TM plates. And after its life of the bridge, it will be 100% recycled to become a new bridge or a new project. And I think this sounds quite like a nice vision where we all could work for. And by that, I want to thank you for your time, and we're ready for questions.
Thank you very much, Tobias, for an interesting presentation. So let's try to come back to the previous presentation of Madhu. So Madhu, please try to present again. Let's hope that it will work now.
Yes, let's try. All right. Can you hear me now?
Perfect.
Okay, very good. Okay, third time lucky. Sorry for that, ladies and gentlemen. Good afternoon or good evening, wherever you're joining from. My name is Madhu Sainathan. I'm a Segments and Application Manager at SSAB, based in Finland in the Nordics here. I will take you through today the fossil-free steel for bridge construction. And in today's agenda, we will touch upon the challenges that the construction industry is facing today, and as a solution from SSAB is the fossil-free steel and SSAB Zero, and we will also go through the sustainable upgrading concept from SSAB. And if you look at the challenges of construction industry today, and I think the climate change is kind of touching upon us for the entire world, not just for the construction industry, but on top of that, with the increasing population, with urbanization, and more resources are getting scarier, and then there is more need for new and infrastructure. So, which means that construction cannot slow down, and there will be more and more building and bridges that would be built. And in the end, construction industry is responsible for 39% of the global CO2 emissions. And what is interesting is, out of these 39%, 11% of those emissions are from the embodied carbon. And the major part of that is, of course, the operational carbon that is during the use of that. And if construction industry has to decarbonize, it is important to address both the operational and embodied carbon. And what is embodied carbon? It's the carbon footprint of the materials that gets into construction in the entire life cycle. It is starting from the production of the raw material till the the construction is taken away. So it's an entire life cycle of that. And how do we reduce the carbon footprint of the the material that gets into it? And that is, there are many solutions, and today we are going to talk about three options from SSAB. And how steel and construction are related. And I think this is no brainer, because steel is used extensively in the construction industry. About 35% of steel's use in Europe is coming from the construction industry, and therefore steel has a big role to play also in the carbon footprint of construction industry. So much so that if we consider the Swedish construction industry, about 21% of the CO2 emissions from the Swedish construction industry is from the steel, both the construction and the reinforcement steel put together. And how do we address this? Are there one specific way to do it? Well, there are different options. If we look at it, the best way to do is to build nothing. And I think we are not in that phase right now. As you saw, with the growing population, we need to build more. So build nothing or build less, those are not an options for us. And then the options that we have is to build smart, which means try to optimize the materials that we have and be aware of the carbon footprint that these materials come along with, and also trying to be more efficient in constructing whatever that we are up to. But building smart is the goal, and that is by using or designing the material that has lower carbon footprint. And I would like to say that carbon footprint is not a nice to have anymore, and carbon footprint of the materials that is getting into construction is becoming a product development parameter. And also, I would go one step ahead in saying that when you're designing a building or a bridge, so then carbon footprint will be one of the most important design parameters in the future if construction industry has to decarbonize. And as a steel user, as a part of the value chain, there is a responsibility for the end users in trying to reduce the carbon footprint, not just of the construction industry, but also of the steel industry, by demanding for greener products. And how do we do it? Is there one solution? And I think my previous speakers, they also touched upon the different ways of producing steel. And today in the whole world, the demand for steel is about 1.8 billion tons. And then moving forward in 2050, it's only going to go up. So the share of recycled material is only so much that we can't use, it won't be enough to cover. So we need a mix of both steel making, both from recycled steel, but also from the virgin iron ore to decarbonize the steel industry, and in turn decarbonize the end user industries like the construction, which is one of the biggest steel users. And the answer from SSAB are two-pronged. One is SSAB 0, which is based on high quality recycled steel, and we would be using fossil-free electricity and also fossil-free fuels in the entire value chain of the product, as well as in the internal transport. And when we move to the fossil-free steel, then that is the sponge iron based, that's from the iron ore based, from the virgin iron ore. So there is no fossil fuels used right from iron ore till the end steel product there. So we have both the technologies that we want to bring up. Like I said in the previous slide, there is no one solution. So we would need both the recycled steel as well as the virgin iron ore based steel to try and decarbonize the steel industry. And we will touch upon both of these one by one. To start with the fossil-free steel, and when we say fossil-free, it is fossil-free in the entire value chain of the steel. So we start from the fossil-free iron ore pellets from LKAB, which is one of the partners or the stakeholders of hybrid. And then we move from using the pellets and hydrogen. So we produce the sponge iron or the direct reduced iron using the hybrid technology, which is fed into the electric arc furnace along with some recycled steel. And then the further downstream process of secondary metallurgy and then the steel rolling. And hybrid is a joint venture of SSAB, LKAB, and Vattenfall, which started in 2017. And the pilot plant has been in operational since 2020, and the demonstration plant has also been started. And we plan to reach about 1.3 million tons of fossil-free HBI, or the hot briquetted iron, by 2026. And the fossil-free steel has already been rolled. In fact, last year, we delivered about 500 tons of fossil-free steel to our customer partners. And there are many customers who have joined hands with us to try and decarbonize their value chain, to reduce their scope 3 emissions by using our fossil-free steel. And if we try to compare how is the new process of fossil-free steel to the existing one. So today we use the iron ore pellets, and there is already some CO2 emissions during the pelletization process. And we also use, of course, the coke as the reducing agent in the blast furnace. And because of cokes, there is, of course, the CO2 emissions in the blast furnace, and then we have the secondary metallurgy after that. But when we compare this to the hybrid process, we use renewable electricity and water to produce hydrogen, which doesn't have any emissions. And this hydrogen is used as the reducing agent along with iron ore pellets in the sponge iron facility to produce the DRI, and that's fed into electric arc furnace along with some amount of recycled steel. So that is the process of the fossil-free steel. And in this process, both in the upstream and downstream, there are no CO2 emissions as well. And by 2026, we will have the commercial availability of fossil-free steel. And moving on to the next one is the SSAB 0. It's the recycled material will be the raw material for this. But again, here as well in the value chain, when we consider scope 1, scope 2, there won't be any carbon emissions. And it's not completely zero, but it's so little that when we round off, it's almost zero. And when we consider scope 1 to 3, it's about 0.3 tons per ton of steel. And we are the first to introduce the fossil-free steel in the market. As I said, by 2022, in 2022, we sold already 500 tons. And we plan to go fossil-free the entire operations by 2045, which has been brought forward by 15 years, so by 2030. So we would like to go fossil-free in our entire operations. And some of the customer partners, we have customer partners in different industries, but to touch upon the construction, which is more suitable for this forum, is some of these names that are more familiar in the construction industry, and they have tied up with us for reducing their Scope 3 emissions. And moving on to the last solution of sustainable upgrading to try and decarbonize the construction industry. Sustainable upgrading is about using high strength weathering steel where there is no need to hot dip galvanize, no need to paint. And then when high strength steel is used, as the other speaker said, so there is a reduced embodied carbon, and also there is the ease of using and also savings from welding and so forth. And we call this as using steel better. And I don't need to explain so much about weathering, and the natural patina is acting as a barrier to reduce the rate of corrosion. And in some of the studies, it has proven that weathering steel has the lower life cycle cost as compared to painted steel or compared to the galvanized steel. And that's also one of the reasons it is called a sustainable upgrading when you use painted carbon steel as and then upgrade it to weathering steel, especially if it's high strength. And to give an idea of how much CO2 emissions could be avoided by moving from painted or galvanized steel to weathering steel, for a given thickness, it's about 120 kgs of CO2 emissions that is released by batch galvanizing a ton of steel. And when you paint, depending on the paint coating, so this is 320 micrometers in C5 environment, it's about 160 kilograms of CO2 emissions that is released by painting a ton of steel. So these are avoided with weathering steel. And then, of course, when you upgrade from low strength to high strength weathering steel, so in SSAB we offer weathering from 355 yield strength megapascal levels to up to 960. So there is a big scope of reducing the amount of steel that you use, which not just helps in fabrication, but also reducing the amount of steel you use, and thereby also reducing the embodied carbon. I would like to say that SSAB weathering offers one of the most sustainable options in reducing the life cycle embodied carbon of construction industry. And some of the examples of bridges that we have been part of, there were also quite many bridges, but for the time constraint, I selected a couple of them. This is one of the bridges in Finland, built in 2021, and also winner of the Best Bridge Design Award. And this is a bridge that is right now under construction. That's why you see the animated picture here. It's in Uppsala. It's a bridge that is openable and whereby the boats can pass through this stream, and they chose weathering steel for its sustainability aspect here. And also when you use weathering steel over a water body and when you repaint, so there is no risk of covering the bridge, and the water is not polluted by the paint or the paint debris. And we have a quite wide product portfolio in weathering steel, starting from hot rolled plates up to 460 megapascals. Then we also have in hot rolled strip and cold rolled, and as well as in the tubular and profiles as well. And this is the first fossil-free steel that was rolled in 2021. And the Ministry of Sweden were also present in that ceremony. And I'd like to inspire by saying that this is the first a mining truck made using fossil-free steel, and we finally hope that this will be expanded to many other industries. So I'd like to conclude by saying that the prospect of building a bridge with fossil-free steel in the future is not far away. And I urge you to mention the carbon footprint as one of the parameters in the design. Ladies and gentlemen, thanks for your time.
Thank you very much, Madhu, for this interesting presentation. And I think that now we have sufficient time for questions. I was watching the Q&A folder, and I think that the majority of the questions were focusing Mike. So I would like to start with the first question from Tim Collins. The question is, Mike, are upstream scope 3 emissions not included in the ArcelorMittal calculations? If not, can you explain why the cradle-to-gate emissions profiles are commonly requested?
Yes, upstream scope 3 emissions are included in our calculations as well. They are part of the EPDs. So yes, they're included.
Sorry, Mike, do you hear me?
Yes, I can hear you. Yes, yes.
Oh, okay. So I thought that I have some problems with the connection. So is the answer okay for Tim? If yes, that then we can move to the second question. So the question is focusing that Jonathan is interested to know if we have statistics and charts showing number of steel companies implementing BOF, EAF and DRY in Europe or world, and how much tonnage per year and steel they produce.
I may start. I think this is a more general question. I think there are statistics for sure about steel companies implementing different production routes in Europe and also the world. Now, at the right moment, I do not have any statistic in my hand to share immediately, but I guess they can be found, McKinsey or something like this. There should be something similar available. I can check, and if I find, I can share with Jonathan. It's not a problem.
Okay, thank you very much. The next question is, would the use of scrap to make new steel affect the availability of grades and subgrades or other quality aspects to be considered?
Yeah, at the moment, let's say the amount of scrap that is used in the electric arc furnace, if you're talking now about electric arc furnace, the amount of electric arc furnace is quite small right now, so that the scrap is still enough to be used in the electric arc furnace. So there is no shortcut of scrap, and also no shortcut concerning the grades and subgrades which are available. So the steel profiles are normally talking now about ArcelorMittal, but I think also my colleagues can also add. So we do not detect any shortcut in any availability of a steel grade or scrap at the moment.
And I think it's a little bit related to the next question, if there is a sufficient and reliable supply of highest quality scrap, and if you will not end up with the insufficient amount of scrap from the structures.
Yes, we also bought some scrap purchasers, so that in fact we can ensure that we have a reliable supply of high quality scrap. So this is ensured.
The next question is focusing the cost. So if there is an additional cost to be considered for X-Carb steel,
yes,
compared to the traditional steels.
I'm not a commercial guy, so for me it's difficult also to talk about pricing. But as an order of magnitude for the X-Carb recycled and renewably produced steel, as an order of magnitude, we can say about 50 euros per ton.
Okay. And the next question is regarding the bridge in Rosiers. The box section would seem to create voids that cannot be inspected in the future. Were there any other design considerations taken to convince the client?
Yes, in fact, the box, they are hermetically sealed. So meaning it's really like a hermetically sealed box section. So meaning if you apply a anti-corrosion protection, you also do not need to apply it in the inner part of the box. So in this case, there's not an issue concerning this inspection that there will be corrosion or something like this. Of course, other points which were very attractive for the investors was the ease of erection of the bridge, because the parts were delivered in single parts and they just need to be lifted up. As at the construction stage, it was really to lift them up as a row of single span elements. And then the continuity was realized by concrete crossbeam, which was concrete at the same time as a concrete slab. And so the continuity was ensured then in the later stages. And by doing so, we could also deliver the beams in one single part. So there was no welding or bolted splices necessary on site. So it was quite easy to erect and to fabricate. And that was also one argument why they decided to go for this solution. And it was also a quite light solution compared to the initial one.
So you are talking that it's quite low cost. So it's connected to the next question. What are the construction costs? And if it's cheaper to build the bridge using X-Carb steel or composite or concrete girder structure?
Yes. About the construction costs, I don't have the numbers now in mind, but generally speaking about the construction costs, okay, even they are not the main, let's say, factor which should be taken into account for bridge structure. You should more apply also an holistic approach, so meaning also seeing what could be the secondary costs coming from, for example, if you need to maintain the bridge, you need to block the road below the bridge to repaint or something like this. So, or also during construction stage, if you have higher period where you have to block the traffic below, this also generates costs. And also how to erect the bridge on site, if it is difficult or not, all this counts. And in fact, here it was a mix where finally it turned out that this was in a mix, if you apply the holistic approach, was the best solution. About the construction costs, normally you could imagine that they are quite similar at the beginning, but if you make the LCA and LCC, you will see that the steel solution was the better solution in this specific case for this bridge. You are on mute, Pavel.
Okay, sorry. Thank you very much for this answer. And we have also other questions. And then maybe this one could be answered by Tobias from Jonathan Peralta. Is there any law in your country mandating steel producing companies to maintain or limit steel production per year? And how does your government monitor carbon footprint on projects and some actions taken?
Yeah, hello. Yes, actually, I'm not sure whether I can answer this question because of producing companies to maintain or limit steel production per year. I mean, of course, there are statistics on the steel production in any year in every country, but I do not think of laws that limit steel production per year. Maybe some of my colleagues can add something here, but I actually do not know exactly how to answer this question. Yeah.
Well, it's not the, if I may come along, it's not the limit on the steel production, but it's through this emission trading system.
Okay.
So that's kind of the regulation that we have,
yep.
Which will be the number of free allocations would be taken away gradually and would be made zero, I think sometime 2030 or 2034, I don't remember, but that's the one thing that kind of drives or makes all steel companies to decarbonize. Otherwise, it'll get expensive. Yeah.
Okay, anything to add from someone else, from Mike, for example, to this topic? Because it's quite general. It's not on one company. It's focusing more aspects.
Yes, I think I can just agree with what Tobias said. I think it's difficult to have an answer right now. I think it's under development, and it's for sure that rules will come sooner or later. And depending on the country, of course, sooner or later. If you see, for example, in the Netherlands and in France, they also have some, well, they start to develop those rules, and there are already some rules also in the Netherlands concerning tender phases, where you can get exceed slightly, where you get weighting factors concerning the maximum budget that you can have, depending on how the CO2 embedment is. So I think it will come. But now to see how it will be in 2 or 5 years, it's difficult. There, I don't have an answer right now for the moment.
Okay, so I think this one was answered. We have another technical question. If you build a pedestrian bridge over traffic in weathering steel and you have to provide drip pens to avoid staining cars with the dripping rust color from the steel, do you have any advice for those situations? If you build the nice weathering bridge over the river, it's fine, but if it's in this environment, it's much more complicated. So how to avoid those drips of the rusted color on cars, on people, and so on. So I don't know who would like to answer this question. So it's maybe for all of the speakers, because it's generally it's covering all of them.
Yeah, if I may start. So, okay, I know not now exactly the detail of the bridge. What I can say, there is this European design guide for weathering steel from ECCS, which has been published, I think, 2 years ago, and which give some indication how to detail at the abutments, how to form, for example, stiffeners to avoid that you have a dripping off of these rusting stains on the abutments, respectively below the bridge or under the bridge. But of course, I'm also fully open to discuss with Mr. Dante Luis in more detail to get the details of the bridge and to have a closer look on it, of course. But it's right now difficult to see. But I also agree with him that wonderful bridges over a river in weathering steel is always perfect. It's a really nice way, if you keep the distance between the water surface, to have a such bridge.
Also, if I may add to that, Pavel, that
Yes.
It's only for the initial years till the patina layer stabilizes this rust staining issue, and once it's stabilized, there won't be any rust runoff. And also, I don't think the cars will be stationary under the bridge, so they will keep moving. So the amount of stain on the cars, I don't know how much that will be there, but perhaps it could be an issue, but it's only for the initial years till the patina layer stabilizes.
Okay, thank you. So I think this was also answered. We have another question, but I'm not sure if it's a question or comment, but I will ask about it. It's from Jaroslav Odrbňák. All green solutions should be confronted not only from the point of view of the CO2 footprint, but also from the point of view of the costs. You have compared the total lifetime costs, including maintenance, demolition, waste, when using patina steel 420 versus classic 350 or S420. For example, in the case of one of the presented traffic objects. So I think it's the question if you did this comparison in your study. I think it's maybe for Mike.
Yes, so what I showed is, of course, for this bridge, it was a comparison of the CO2 footprint because it is in line with our topic of today to speak about sustainable bridges. And I agree with this comment. Of course, the costs are also an important factor and they should be compared. And I think we have, all the information to do it. And I think this is also what we do. Now, I did not present it today, but of course it is in our mind. And the construction costs, of course, a very important factor also for the decision for one or the other variant. But this then strongly depends also on the project.
Okay, so thank you very much for that. Maybe I have one question to Madhu. You were mentioning the high strength steel made from weathering steel, and you were showing the grades up to 700 megapascals and so on. What about the fatigue behavior of those materials? Because generally we know that weathering steel is a little bit worse in case of fatigue than the conventional steel. And if you increase the strength, then the fatigue becomes a much more important issue. Did you do any tests? Do you have some information that is related to the topic?
Yeah, that's a good question. And I think one thing I would like to say is weathering steel is also structural steel. So it's not very different to the conventional structural steel in that sense. But when it comes to fatigue, I think it's basically because of the Euro norm that says that the weathering steel should consider one fatigue class lower as compared to the normal steel. But in our opinion, I think the surface of weathering steel has the only problem that you have in fatigue is not the lower fatigue life in itself. The problem is during the maintenance in identifying or locating the fatigue cracks when there is a patina layer. So the design rules for weathering steel could be the same as that of the carbon steel. The only problem is identifying the fatigue cracks, and for that also there are research reports available how to identify the fatigue cracks. So if somebody's interested, then they can get in touch with me on that.
Okay, so thank you very much. I'm going through the Q&A, but I think that maybe all of the questions were answered. Some of them maybe directly by the speakers. So I think that is all that we can ask. So if there are no other questions, I would like to thank again to all our three speakers. Thank you very much for very interesting presentations. Thank you very much for your time. And also I would like to thank all the participants that were attending this webinar. I think we had a very nice number, almost 100 participants in the webinar. So thank you very much again, and I wish you a very nice and pleasant weekend. Thank you and goodbye.
Yeah, thank you.
Thank you.
Thank you.
Goodbye.
Bye.
Yeah.
Good weekend.
Bye-bye.